Look around the room you are in right now. A coffee mug on your desk will remain perfectly still until you push it. That is a foundational rule of physics. An object at rest stays at rest unless an outside force acts upon it. We can measure exactly how that push works. The relationship is defined by a simple equation. Force equals mass times acceleration, or F equals ma. To get an object to move, you have to apply a physical force proportional to its mass. Hold a pen in the air and let go. It immediately accelerates toward the floor, gaining speed with every fraction of a second. According to the rules of motion, a physical force is pulling it down, even though there is no visible hand doing the pushing. This invisible, relentless downward pull is gravity. It's an active tether, constantly dragging every piece of mass on this planet toward the Earth's center. In this environment, true stillness is rare. Even when your coffee mug looks motionless, it reacts to this force, pressing down with exact mathematical precision. When gravity is the absolute and only dictator of an object's movement, physicists define that state as freefall. Dropping a pen in a standard room fails the definition of a true freefall because of the environment surrounding the object. In this diagram of a falling object, we see the massive downward force of gravity, but air resistance pushes back up. By removing the air to create a vacuum, we eliminate atmospheric pushback, leaving only a single, uninterrupted downward vector. Stripping away the atmosphere reveals motion driven by gravity alone. We can translate our general rule of motion into a specific rule for gravity. That rule is weight equals mass times gravitational acceleration, or W equals mg. To understand this, we have to separate mass from weight. Mass is the constant amount of physical matter packed inside an object, measured in kilograms. Weight describes the actual physical force of the Earth pulling on that mass, which we measure in newtons. Because common scales use kilograms or pounds, we often assume our weight is a fixed property of our bodies. This model shows why weight is actually variable. The Earth is not a perfect sphere. Because it is constantly rotating, the planet bulges outward at the equator and flattens at the poles. Standing on the equator places you physically further from the center of the Earth than standing at the North Pole. This distance alters the gravitational acceleration pulling on you. At the poles, you accelerate downward at 9.832 meters per second squared. At the equator, that value drops to 9.78 meters per second squared. This effect compounds with altitude. On a massive peak like this, increased distance from the Earth's center further reduces the gravitational pull on your mass. Your weight shifts based on your exact coordinates, fluctuating as your distance from the center of the planet changes. The Moon presents a specific question. If Earth's gravity pulls objects toward its center, why hasn't it collided with us? The answer lies in tangential linear velocity. The Moon is traveling sideways at extreme speeds. The Moon is in a perpetual state of free fall toward the Earth, reacting to gravity exactly like a dropped apple. In this diagram of circular motion, object A moves at a constant speed along its path. When extreme sideways speed combines with a downward fall, the resulting path is a circular orbit. The Earth's surface curves away at the same rate the object falls. In this follow-up, we can see the direction of the force. This constant inward pull, directing the object toward the center point C, is called centripetal force. Orbital mechanics describes an object falling perfectly sideways, maintaining its altitude as the planet beneath it curves away. Newton's universal law of gravitation expands this rule of attraction far beyond the Earth. The law states that every object in the universe attracts every other object. The strength of that attraction is determined by the mass of the objects and the square of the distance between them. This means you are exerting your own microscopic gravitational pull on the device you are watching this on, just as it pulls back on you. From a dropped pen to the Moon's orbit, every movement in the universe is a mathematical response to the invisible forces binding the cosmos together.